Hi, welcome to the notes for 8.2.1. This section is titled the number E, and we're looking at part 1 today. This will span several lessons, so you'll get a little bit today, a little bit in the next lesson, and so on. Early in the chapter, we investigated the idea of the dominant terms to evaluate limits of rational functions. Okay, so today, when we're starting out, we're going to just review and think about our exponential functions a little bit. So you'll see that we have four functions listed on your paper. Y equals 2 to the power of x, y equals 1.5 to the power of x, 1.1 to the power of x, and 1.01 to the power of x. Now, some characteristics I hope that you see is that each of our bases is greater than 1, right? So 2 is like twice as big as 1, and then on the right side you have 1.01, which is just slightly bigger than 1. Okay, so when we think about our exponential functions and what their graphs look like, right, let's just go ahead and graph them on the calculator. So you'll see I already have these typed in, but I'm going to just activate them. So the first one, y equals 2 to the power of x. When I graph that, you'll see we have our exponential curve. Right, I'll even zoom in a little bit. Right, and it crosses through that point 0, 1. And then when I go back in and let's activate our 1.5 to the power of x, this one will be the green graph. You'll see that it also has exponential growth, and it also crosses through that point 0, 1. And you know what? Let's go ahead and start graphing these on our paper. So y equals 2 to the power of x. I know that this is going to come from down here, and then it's going to make a steep turn and then go up like this. It's growing exponentially. Our second function, the 1.5 to the power of x, right? You notice that you can see it a little above here. It's a little bit more horizontal, but then it goes through that same point and it goes up this way. And if you were thinking about which of those functions would win the race to infinity, obviously 2 would because the base is bigger. And let's go into the next one, right? We have that 1.1 to the power of x. This one will show up pink on my graph. And you'll see here, this one takes it a little bit longer to get up there. So as it's going through, and I'll actually make that one pink on here as well, right? So you see it's a little bit more horizontal, and it takes this one a little bit longer to curve upward. And then obviously our last one on here was that 1.01 to the power of x. So I think you probably know what this one's going to look like, right? This one's much more horizontal, but it does start to curve and head up that direction towards positive infinity as well. So I'll make that one green on here, right? So that's this one, but this one's much more horizontal, and it takes it a lot longer to get up there. But remember, in all of these, right, they are going up to the right because the base value on each of these is greater than 1. So if you think about also, like, what if I just put in, like, y equals 1 to the power of x, right? When we think about 1 to the power of x, we're thinking more like, almost like a straight line. Well, it is a straight line. They're all straight lines, but it's a horizontal line, right, that would run that way. So because these values are greater than 1, it means that they are increasing. And if those values were less than 1, like a fractional number, we know that then we would have exponential decay. These are things that you've seen in the past. All right, so with that in mind, let's move on to the next slide. Okay, so the first set of problems we're going to do are review. You've seen these probably as far back as in Algebra 1. We're going to look at exponential growth and decay using that function y equals a times b to the power of x. And remember, when you learned this, a was always our initial value, or sometimes you called it the starting point. And b, we said, was our multiplier. Okay, so when we take a problem or a scenario like a $450 investment grows at a rate of 2% each year, how much is the investment worth after 18 years? Well, the amount that it's going to be worth is going to equal our initial amount, 450, times our multiplier, right? So what is our multiplier going to be if it's going to increase by 2% each year? If it wasn't going to increase at all, right? If it was going to stay at 100% of its value each year, we would multiply it by 1. We need it to grow, so it needs to be greater than 1. And remember, 100 plus 2, right? 100% plus 2% is 102%. But we don't write it as 102%. We write it in decimal form, which would be 1.02. And we're going to raise it to the power of 18. So let's jump out of our graphs and we'll just type this in. 450 times 1.02 raised to the power of 18. And we get $642.71. Okay, so at just 2% each year for 18 years, they gained about, what is that, 100, like almost $200. Okay, let's look at the next problem. A $26,000 car depreciates at a rate of 9% per year. How much is the car worth after 6 years? So remember, depreciates means it's going to decrease. We're losing 9% of its value each year, which means it's holding on to 91% of its value. So when we put this one into the formula, we would say y equals 26,000 times our multiplier, which would be 0.91. Remember, it's keeping 91% of its value each year. And then we'd raise that to the 6th power so we could figure out what it would be worth after 6 years. And you can go ahead and use the calculator again, right? 26,000 times 1, I'm sorry, not 1, we'd have 0.91 raised to the 6th power. And our car is now worth $14,764.60. All right, so hopefully those ones look familiar to you, like you've seen those in the past. Okay, so this formula relates to what we were just doing here, and we're talking about simple interest or depreciation, right? You'll see this formula written. This is the same kind of thing as the y equals a times b to the power of x, but this is when we're looking at simple interest a little bit more, or depreciation. So our a, right, is going to be, let me change colors here, right? Our a is our new amount. I'm going to write new in front of it, right? It's our new amount after we've done our calculations. Our P we know is our principal. It's spelled like the person, right? And we've got that's like our initial amount. So it's like our little a from up above. And then, the 1 plus the rate. So that's where our rates were coming from up above, right? This is like 1 plus 0.02. Right? And then, the one down below, since it's depreciating, right, we'd have like 1 plus a negative, or you could say minus, 0.09 on that one. Okay, so we know here that our rate is always going to be written as a decimal. And then T, we know, is going to be time. And usually, in this case here, when we're talking about simple interest and depreciation there, right, that's usually given in years. We're looking at years. Okay, so that formula kind of relates to both of these problems. We just probably are more used to seeing it in this form when we see those. Now, there's another formula, okay, that you probably saw back in Algebra 1 a little bit. Maybe Algebra 2, I don't remember if we talked about this at all. I know I had some of you in Algebra 2 in the past. So if not a big deal. We're going to go through it right now. So most investments are calculated with compound interest. Okay, so this is much more important in terms of real life. When we're talking about investments, banking, financial stuff here, okay? We use a lot more compound interest. And what compound interest is, right, it's like when we're investing money and we're earning interest over time, okay? So instead of compounding it one time each year, we compound it several times over the year, or, it just depends on the situation. But you're able to compound the interest So you're going to earn interest on the interest you've already earned that year. Okay, so this is a way to make your investments and the money grow faster. And you'll see this formula is very similar, right? We still have our new amount out in the front. We still have our initial value or our principal, right? 1 is like that 100% that we would start with. You know, our R is still our rate as a decimal. And then you'll see here we have a new variable in here, right? Our N values, right? And what N represents when we do these is the number of times we're going to compound the interest per year. Okay, so it's the number of times we're going to be compounding the interest rate, or we could say calculating. Okay, the number of times we're going to be calculating. That's just another word for compounding the interest per year. So rather than just doing it one time at the end of the year, we're going to compound or calculate the interest earlier in the year, and then it's like you get that amount added to it there. So it's like you get a little bit of an increase each time. Okay, so it gives you a little bit more in the long run. And then obviously, oh, I'm sorry, I forgot about T. T is our time in years. So let's use this formula a little bit. Here's an example. We have Miranda plans to invest $5,000. Bank A has offered her 5% interest compounded quarterly. So Bank A, 5% interest compounded quarterly. So that means they're going to take that 5% and they're going to compound it 4 times throughout the year, right? Quarterly be 4 times. So they're going to kind of break it into 4 parts and they'll do a little bit of it at a time. Now, our Bank B has offered her 4.85% interest, but they said that they will compound it daily. Okay, so they're going to compound it each day. And if you think about over the course of a year, if it's not a leap year, they're going to compound it 365 times, but at a lower interest rate. Okay, so we're going to try to figure out what bank Miranda should use or choose for her outcome after 5 years. So let's look to compare these. So we're talking about Miranda. I don't really need to write her name down, but we'll just talk about Bank A. And then we'll calculate Bank B, and we'll see which one is better. So we're just going to use our formula from the other page, right? So her new amount is going to be equal to her initial amount, which was $5,000, times 1 plus, and then our rate, remember, was 5%. So since we're just compounding the interest quarterly, right? We're not compounding the 100%, just the interest that she's earning, right? We got to write that as decimals. So that'd be 0.05. And we're putting that over 4 because it's going to happen 4 times over the course of the year. And so since we're breaking into that 4 parts, we're going to multiply that 4 times our 5 because this is going to happen over 5 years. And we can just take this here and type it into the calculator to get our value. So we'll say 5,000 times 1 plus 0.05 divided by 4. And then we're going to raise that to the 4 times 5th power. And you'll see that her investment of $5,000 will then be worth $6,410.19. Okay, so she made some money there. Let's try Bank B. So her initial amount was still $5,000, but in this case, her interest rate was 4.85%. So that would be like saying like 104.85%. So that interest part of it, we know would then be 0.0485. And we're going to be dividing it by 365, right? Because they're going to compound it each day. So we're breaking that interest into 365 parts. And then we know that it's going to compound 365 times over the course of each of those 5 years. So let's type that in, see what the answer would end up being. We've got 5,000 times 1 plus 0.0485 divided by 365. And then we're going to raise that to the power of 365 times 5. And you'll see Miranda's investment will now be worth $6,372.05. So in answering that first question, which one would be the better option for her over 5 years? I think it's pretty safe to say that Bank A, right, is going to give her more money in the long run in that 5 years. Okay, but let's talk about the long run here, right? Is time really going to matter? Because it asks us this question: will your answer change if the amount of time changes? Let's calculate and see. Right, let's first do 1 year. Let's do 1 year. So I'm going to go up here in my calculator. I'm just going to highlight it. Right, the only thing that's going to change in this expression, right, instead of 5 years, I'm going to change this to 1 year. And it looks like after 1 year, her $5,000 is now worth $5,254.73. Let's go up to Bank B and let's change this to 1 year and see what the output would be. $5,248.46. So it looks like Bank A is still the better option at 1 year. Let's extend it out a little bit. Let's go to 10 years. Let's see what it would look like in 10 years. Okay, so go here. We're just going to add a 0 on. In 10 years for Bank A, it's worth $8,218.10. And in Bank B, at 10 years, $8,120. So it looks like Bank A again. So I think we can conclude from this here that will our answer change if the amount of time changes? No. Okay. Bank A is going to be the better deal. Okay, and then I guess, yeah, we didn't write down there that Miranda should choose Bank A, right? If you want to write that on there, you can. Maybe you already did. All right, so let's move on. The next problem says, suppose that an account earns 5.75% annual interest compounded monthly. Okay, so we're earning 5.75% annual interest compounded monthly. How much would you need to invest initially if you want the account to be worth $10,000 after 20 years? So we want it to end up equaling $10,000 after 20 years. Okay, so what we don't know is our initial investment, right? How much do we need to invest initially, or what is our principal, right? This is our principal. We don't know what the principal is, but we can still use that formula to help us solve this, right? So we know at our new amount, we want to be $10,000. We don't know exactly what we're going to invest yet. But we know that when we do, we're going to be having an interest rate of 5.75%. So when we write that out, that'd be 0.0575. And the number we would have to divide it by if we're compounding monthly would have to be 12. So we're going to break that into 12 parts. That way we can compound it 12 times. And this is going to be over 20 years. So we're going to do it each year for 20 years. So I think you can probably see what it is we're going to be trying to find, right? We're trying to solve it for P. And probably the easiest way to solve it would be to just go ahead and divide each side by the expression that's given there, right? If I do that on the right side, I need to do it on the left side. So we have 1 plus 0.0575 over 12. And we're raising that to the 12 times 20th power. Now you can take it and kind of calculate that down, but please be careful about rounding it, right? If you round these numbers, because you know they're going to be long decimals, you're going to change your answer. So when I do this one, I'm going to go ahead and just do 10,000 divided by, in parentheses, 1 plus 0.0575 divided by 12. And then I'm going to raise that part of it to the 12 times 20th power. And you'll see that the initial investment that we would have to have would be $3,175. And it looks like we'll have to round that up to 8 cents, right? Because if we leave it at just 7 cents, we would not get to our 10,000. So that would be our initial investment, $3,175.08. All right, now we're gonna go off. I don't want to say not on a tangent here, but we're gonna kind of change the subject here for a moment. We're gonna look at, given the following limit, as n approaches positive infinity of our function 1 plus 1 over n to the power of n. Okay, so this is our information that we're going to start talking about in terms of the number e. Okay, so we're just going to introduce it today. Tomorrow we'll talk a lot more about it. But it says here, for letter A, as our value of n approaches positive infinity, what happens to the expression inside the parentheses? It's referring to this, 1 plus 1 over n. If we take this expression and we start to put in values of n, right? Let's say in the first one here that we put like 1 in for n. I'd have 1 plus 1 divided by 1, which is going to give us 2. Okay, now let's see here. Let's increase that. Let's make it 10, right? Instead of 1, we're going to make it 10. We'd say 1 plus 1 over 10. Well, 1 plus 1/10 is going to give us 1 1/10. So as n is increasing, our value looks like it's starting to decrease. Let's put another number in there. Let's make it a little bit bigger. How about 100? So 1 plus 1 over 100, 1 plus 1 100th would be 1.01. Okay, let's go a little bit more extreme. Let's say, what if n was 1,000,000? Right, so as we take it and we do that here, we'd say 1 plus 1 over 1,000,000, right? And that looks like it would equal, what would that be? 1 1/1,000,000th, so tenths, hundreds, thousandths, 10,000ths, 100,000ths, millionths. So if you look at these values, as we start to increase n, these numbers that we're getting out are getting closer and closer to what number? Right? So we'd say as n increases, that's supposed to be an r, our expression inside the parentheses, I'll just put parentheses there because I can't spell it. All right, so as n increases, our expression inside the parentheses becomes closer to the value of 1. Right, so as we continue to add more and more zeros in there in between the decimal and the 1 there, right, they're becoming smaller and smaller pieces. Now, part B says, as n approaches infinity, the increasing exponent causes the expression to get bigger, and the expression inside the parentheses will be getting slightly bigger than 1. It says, therefore, the limit might be, well, let's think about it, right? So if you're thinking about, 1 plus 1 over, let's even do like, let's say we had like, you know, 1,000,000 down here, right? And then we were taking it there and you raised it to, you know, the power of like, say 1,000,000, right? So this number here is still greater than 1, right? And when we looked at our like our warm-up problems here, weren't all of our bases all greater than 1? Right? All of these bases are greater than 1, but you'll notice, right, as they got closer to the value of 1, the more they kind of straightened out here and started looking like this line, you know, where y equals 1. But let's see if this has that same effect here, right? So since the limit for all of these expressions, right, as x goes this way forever, we know that our limit for these would all be a positive infinity, right? Because they're going up forever. So I would say that would be a logical guess. We could say that we think it might be a positive infinity. Okay, but we want to know, like if I took it here and I put in something like, you know, 1 plus 1 over, like say infinity, raise it to like the power of infinity, right there, what is that going to be? So we can actually take this here and we can find this limit using the graphing calculator. Let's do this. Okay, so we want to know, what is this going to equal? So let's get out our calculator. I'm going to do it on the left side this time. Let's go into our y equals, and you can, you know, deactivate or clear out any graphs that you have in there. And remember, we can't use n's, we're going to use x's, but I'm going to say 1 plus 1 divided by x, and then I'm going to raise it to the power of x. And when we graph it, looks a little different, right? Looks a little different. Okay, but we're focused here on this right side. Look, as we're approaching positive infinity, does it look like it has a horizontal asymptote possibly? It doesn't look like it's going up. If it is, it's going up really slowly. So let's kind of figure out what this is going to be. We can use our table probably to get a better picture of what it's going to be. Let's first of all go into our table set. I'm going to set my table up to start at 0. And then since we're going to infinity, we want to take really big steps. I have 10,000 in my calculator. Okay, so you could have whatever you have. But I'm going to press table. And you see on the left side here that like our values are increasing by 10,000 each time. On the right side, you'll notice that we get this number. We have 2.71825, you know, and then it keeps going. So let's scroll down here and see what happens to this number. It's like just the back digits are changing for the most part right now. Right, so we could say here that the limit that we're getting for this one would be about 2.718, and then we could say like 28. Right, we know this is going to go on forever, so we'll just kind of leave it there for right now. Okay, now this value is a really important value in mathematics. Okay, and some of you may have seen it before, some of you maybe not. Okay, but this value is super important. It's like, you know, everybody knows that pi is equal to like, you know, 3.1415, I think like 9, yada, yada, yada there, right? Okay, well, this number is also irrational and it's going to go on forever. And it also has a special symbol that's used as well. That is E. Okay, so when you see this number E, you know, is a little bit less than 3, 2.71828 there. Just like pi is a little bit more than 3. So, but this is a very special number that's used a lot in like real life mathematics, any kind of financials, investments, banking, all that kind of stuff there. It appears a lot in nature as well. Okay, so we're going to spend some time learning about E in this chapter and how it's used in, you know, some of the math concepts. So this is just the last slide. I know it's probably been a long lesson again, so let's get through it as quickly as we can. It says, this somewhat surprising limit is known as the irrational number E. Okay, we already said that. It says find the E button on your calculator and use it to write E out to 9 decimal places. So real quick, when we jump back here, right, we did write that like our limit was equal to this. So we could say that our limit actually equals E, right, because that number is E. But to find it on your calculator, if you have an 83 or an 84, you'll find that E button to the left of number 4. You'll press second, and then you'll press, what we have, the ln button, which is like the natural log, but you'll press second, that you'll see an E, and then we'll always put a little exponent up there. You can just put to the first power, and you'll see there is our value of E. Right, we have 2.718281 828. I think that's 9 digits right there, but it does keep going after that, right? It'd be like, I think it goes 4, 5, 9, and then keeps going. But we're just focused on those first 9 decimal places right now. Okay, so on your inspires, you will find the E button to the left of number 1. Okay, so it's on the left side of the calculator. You'll see e to the power of x. You can just press that there and put a 1 in for the exponent to use that button. Or you can press the pi button. Okay, if you press the pi button, it will also give you the option to look at e. I just don't have the ability to do that on the iPad. Okay, so let's just find the values of a couple expressions here. So we have e squared minus 2, and they want us to round it to the nearest thousandth. So e squared minus 2, and that looks like it would be 5.389. And then let's do the second one, negative 5 divided by e, and then we're adding 3 to e. When you think about it, we know that e is like almost 3, so it's almost like negative 5 divided by 6. Our answer should be a decimal value less, I guess, greater than negative 1, right? But less than 0. So let's see what that is. Yep. So we get a negative 0.874. So hopefully you're comfortable finding that on the calculator. Remember, we're going to continue to work with E as we move forward. Tomorrow, we will see how this new number E relates to our interest problems. So please try the homework tonight. Please remember to check the homework help videos that I've posted in case you have questions. And keep working hard. Okay, and I hope that everything goes well.